Hi, everybody. Welcome to the 2021 Cool Roof Rating Council annual general membership meeting and the speaker panel today. This panel is called the Urban Heat Island Mitigation through Cool Building Envelope Surfaces. I'm Kurt Shickman. I'm the Executive Director of the Global Cool Cities Alliance. I'm also a CRRC board member and the Vice Chair of the CRRC Ratings, Codes and Standards Committee. As we go through today, we're going to have three great speakers that will present on their work. We'll have some opportunities for some specific Q&A after each of the sessions, but then at the end, we've got a nice block of time for a discussion or Q&As to cover broader sets of topics. If you have a question, please go ahead and put it in the Q&A box. It's one of the options you have down there at the bottom of the Zoom screen. Rather than the chat, it'll be much easier for us to capture those questions that way. For those of you that are new to the Cool Roof Rating Council, just a quick overview. It's a 501c3 nonprofit organization that was founded in 1998, and it has four basic pillars of its mission. First, to implement and communicate fair, accurate, credible radiative energy performance rating systems for roofs and wall surfaces. To support research into energy-related radiative properties of roof and wall surfaces, including the durability of those properties. To provide education and objective support to parties that are interested in understanding and comparing various product options. And by pursuing this mission, the CRRC will become the recognized informational resource for reducing the urban heat island effect, increasing building energy efficiency, and improving occupant comfort, and mitigating the global climate effects of greenhouse gas emissions. And to that end, I'm very excited to welcome our three panelists today, each of whom has been deeply involved in important and practical work to understand and address excess heat in our cities. So I'm going to introduce each one before their actual presentations, but I'm going to start with our first speaker, Dr. Hazem Rashid Ali. He's an associate professor in the Department of Department of Architecture at the University of Texas at San Antonio. And his research focuses on sustainable architecture and urbanism achieved through the design of high-performance, energy-efficient, and carbon-neutral buildings and communities. And so with that, I will turn it over to Dr. Rashid Ali for his presentation.
Thank you very much, Kurt. Thank you for the introduction. Agriculture was my second choice after architecture. But let me share my screen. And okay. Good. Do you see my screen now?
Looking good.
Perfect. Thank you. Okay, good afternoon or good morning, everybody, depending on who you are. Thank you very much for joining us. It's a pleasure to be here with you to share with you some of the work that we've been doing in UTSA and in collaboration with the city of San Antonio with regard to cool roofs. The project I'm going to talk about today has been going on since roughly 2016. It started small, but it has now grown quite a bit. So several hundred homes have been retrofitted through this program right now. So I'm going to share with you some information about a research component of that project that myself and my team have been involved in. But it's really a much larger project, and maybe it's better to start with a quick overview of what the project is. So the project is called Under One Roof. As I said, it's implemented by the city of San Antonio. It was the brainchild of our former council member, Councilman Trevino. And his district includes a fairly high percentage of underserved, underrepresented communities, people with low incomes that live in homes that aren't really that good in terms of quality. And he had a really great idea. So he wanted the city to go in and essentially retrofit the roofs of these homes for free for the owners, which in itself would have been a huge addition, a huge improvement in their lifestyle, their quality of life. But he, in collaboration with us in UTSA, we thought that if we're going to retrofit the roof anyway, we might as well replace it with a better performing roof. And we settled on using cool roofing materials, which, as you know, is fairly established in the commercial sector, but maybe not as much in the residential side of things, certainly not in San Antonio. And the idea was that at the same time that the homeowners were getting this very substantial improvement in their quality of life, or also through retrofitting the roofs with a better material, we can also improve their thermal comfort. We can also reduce their utility bills, which for low-income families actually is a major component of their disposable income. So it can make a big difference sometimes in whether they can actually keep their homes or not. And we can also have secondary and long-term impacts on the environmental quality of the area as a whole. So it's a fairly large project. As I said, we started with about 11 homes, and we have several hundred of them done so far. So these are the objectives of the program as identified by the city of San Antonio. So their primary objective, obviously, was to maintain the home integrity by addressing roofing needs. So they had observed that many of the homes in this area were in need of retrofit, especially the roofs. Roofs are, when roofs go bad, you get leakage, you get mold and mildew, you get health problems. So certainly there was a need for that. Their second objective was to improve the energy efficiency and reduce the utility bills for these homeowners. And again, the objective was that for this segment of our society in particular, utility bills account for a substantial component of their income, and reducing that by any percentage would be a great help. And then finally, to demonstrate the benefits of cool roofs to builders and residents. And that's really where we came in as researchers in UTSA. So we were hired by the city of San Antonio as an independent third-party verifier to essentially test this project and let the city know whether it actually works or not. And we'll go in more details about what we did in a few minutes. Okay, so this is the flyer that the city used to recruit people. They had several conditions that people had to meet, so it wasn't an easy process. It took us some time to identify potential candidates, especially at the beginning, because the project was not really that well known, and people were wondering if am I really going to get a roof for free and so on. And there was an obligation that they had to keep their home for a certain period of time after the roof gets retrofitted, and some other obligations from the city side. So that took a while. We ended up, again, like I said, with 11 homes, and then we grew to about 150. At that time, we had completed our work. And then at this point, the project, I think they're in the several hundred, 300 to 400, maybe even more, was the last I heard. This is the new roofing material that we've used. So we use the Owens Corning shingle, 3-tap Shasta white shingles with an SRI of 0.31. We had under that the reflective underlayment of solar hide with an SRI of 0.97. That specification was identified by the city architect. So we were involved in the conversations, but ultimately it was governed by economics and how much the city was willing to spend. But even with a 0.31 SRI for the shingles, I think we ended up showing that it can have a substantial impact on the performance of these homes. I apologize. So what did we do? So this is one of the homes that we did. This is one of the homes of phase 1. You can see the home before and after the renovation. The color was a big factor. People were not comfortable with the light color to begin with. It took us a while to kind of talk them into the advantages that this new material can offer to them. But ultimately, again, once several homes got retrofitted and we started reporting out the results of our work and how we're actually improving, reducing the utility bills for the owners, which matters to them quite a bit, I think it was a bit easier to get volunteers in subsequent phases. So as a research team, these are the objectives that the city asked from us. So we had 3 objectives. We wanted to look at attic temperatures. One of the issues that we quickly realized is that not all the homes that we were looking at had central air conditioning. Some of them had window units. Some of them didn't even have air conditioning at all. And we didn't want to exclude those. We assumed, and turns out our assumption was correct, that the larger benefit would happen for those who have central air conditioning, who use air conditioning. But again, since reasonable percentage of our population didn't have air conditioning, we wanted to capture the benefits that those people would get as well. So we decided to use attic temperature as a proxy for that. The idea is if the attic temperature has been reduced, then that would imply that the indoor environmental conditions inside these homes would also be improved, which would, in the case of air-conditioned home, results in less energy being used. In the case of non-air conditioned homes, would result in a better thermal environment, more comfortable environment for the owners. We also obviously were asked to look at the impact of these new roofs on utilities, on their electricity bills. And we also wanted to make sure that the results that we get really reflect as much as possible the impact of the roofs, not any other impact. So, and we took a lot of measures to make sure of that, which I'll go through in a few minutes. So how did we do that? With regard to the roof temperature, we installed data loggers in the attics before and after the roof construction. That was a dynamic process. We had to work with the contractors, and we had to make sure to go into the homes with a sufficient lead period before the construction started to happen. We aimed at least for 2 weeks before construction. Sometimes we got more, but the very least, the minimum that we wanted was about 2 weeks. We were able to achieve that. After construction, usually we could leave it there for longer periods of time, and most of the time we did. So we had an accurate record. We had minute level data of temperature and humidity values inside the attics, both again before the new roof was constructed, which would reflect the original condition of the homes, and then after. We calculated the difference in temperature. We obtained actual temperatures, hourly temperatures from a nearby weather station, about a mile away. And we calculated the difference in temperature between the attic and the outdoor temperature at every hour. And we created an average daily profile of that temperature, both before and after. And I'll show you how the two compare in a few minutes. With regard to utility, we worked with our local utility company, CPS Energy, and we obtained billing data for all of these homes for a minimum of at least 1 year before and 1 year after the roof installation. We added all of this data to Portfolio Manager. Some of you may know Portfolio Manager. If you don't, it is an EPA online tool that is used to assess building performance. So the good thing about Portfolio Manager is that it actually does a weather normalization for the data. So essentially, it cancels out the impact of this year being slightly hotter than last year, or this year being slightly cooler than last year. So we're sure that we're comparing the impact of the roof itself as opposed to what may be an unusually hot year or an unusually cold year. And obviously, using Portfolio Manager, we managed to calculate the difference in the use of energy before and after the installation of the roofs. And then we also did a fairly detailed conditions assessment and survey of the homeowners' patterns of energy use. So we went there and asked them, like, what do they set thermostats at? What types of equipment do they use? We did that before and after, and our goal was to identify anomalies. Or maybe a better statement is to explain anomalies. So when we got the utility data, some of in a small number of homes, the numbers didn't make sense. Like, for example, we saw a couple of homes in which the energy use spiked, which was unusual and unexpected and inconsistent with the rest of the data. So we went back to our surveys and we realized that, for example, in one of these homes, we had 2 people living in the home before the roof was constructed, but they had 4 additional family members join them after the roof was constructed. So obviously the data now doesn't really reflect the impact of the roof, and we managed to exclude that home from the analysis. So we did that with a few homes. And that, again, was one of our control measures to make sure that the data we're reporting out is really reflecting the impact of the new roofs, not any other side effects or other factors that may affect energy use, may have affected the energy use in these homes. My computer is determined not to go in the right direction. I apologize. Okay, so how many homes did we do? We started, as I said, with 11 homes. So that's phase 1A. That was kind of our pilot phase. And then very quickly, we managed to expand to 30 homes. So for these first 30 homes, we did both an attic temperature analysis and a utilities bill analysis. When the city expanded their project, we decided to expand our sample size. But in this time, we focused more on the utility bill size, and this was more of the crucial thing to look at. The attic temperatures showed very positive results in phase 1, so we weren't really that worried about that. We wanted to make sure that our utility information is accurate. So instead of doing 30 and 30, we did 45 additional homes in terms of utility analysis. We did 15 additional homes in terms of attic temperature analysis. So we ended up with 75 homes on the utility side, 45 homes on the attic temperature side. And you can see the time periods in which this was achieved. In terms of attic temperature, I want to point out that we tried to spread them across the year as much as possible. So phase 1A was right at the heart of summer, the hottest period in San Antonio, July to September. Phase 1B was mostly winter, December through February, well, winter. And then phase 2 happened in late spring, early summer. So it was still fairly hot in San Antonio at that point. So let's talk a bit about the results that we got. So starting with attic temperatures, this is phase 1A, our first 11 homes. This is, again, summer installation. The two graphs that you can see represent the average daily difference in temperature before and after. So each one of these gray lines represents one of the homes. The thicker line is the average of all of the small gray lines. And the way you read that is, for example, let's say the before installation line, if you look at 5 p.m., the temperature inside the attic was about 21 degrees higher than the temperature outside. The highest line, the house in which we had the highest temperature, again at 5 p.m., the temperature inside the attic was about 35 degrees hotter than the outside. So imagine if the outside was about 100 degrees, which at some of these days it was, we're talking about 130, 135 degrees temperature inside these attics, so substantially hot. After installation, again, you can see that even visually, you can see that there was a substantial improvement. So on average, again, after installation, we got to about a 10 degrees difference between inside and outside, which is very good compared to almost a 20-degree difference between inside and outside. So if we compare just these two average lines, you can see that we managed to get about, again, a 10.1 degree drop in attic temperature at the peak time, which for CPS Energy, for our utility company, is the critical time. Over the daytime period, even accounting for morning periods, the drop was about 6.3. So that was a very positive result that we were very happy with. When we went to phase 2, which was the winter, and in winter, we really wanted to not see a difference, because a difference in this case would be counterproductive, because the homes need heating as opposed to cooling. So if the attics are cooler, then that means that the house is losing more energy to the outside. And the results came out, again, fairly positive. So again, before and after, you can see that they're fairly similar. And if we compare them, again, you see that we only got about a 1 to 2 degrees drop in temperature in the afternoon, less than 1 degree drop in temperature throughout the day, which again made us comfortable that these roofs are causing a positive impact in summer, but not penalizing the homeowners in winter, which we were at the beginning at least questioning whether that would happen or not. The third period, again, which was April through May, that was a reasonably hot year, and we still got a good improvement in that. And you can see that it was kind of mid-range between the June to September or July to September period and the winter period. So you get about a 6-degree drop in temperature, and in the peak period, the afternoon period, and a 3.6 in the overall daytime period. So in general, attic temperature analysis showed that the roofs actually do reduce attic temperatures on average. Again, some homes got a much better benefit than others, as was expected, but on average, throughout our sample, again, 45 homes, it showed a positive impact in the warmer periods of the year, and it didn't really show a substantial negative impact in the colder periods of the year. So when we went to our utility analysis, and here I'm going to show you the overall results for all 75 of our homes. I think we ended up with about 71 homes included in that analysis, because again, we excluded some of the homes. So the bar that is labeled all homes is actually all 75 of them, but that bar is not the one that I look at, because again, that has the anomalies that we have identified through the surveys. All homes except excluded is the more accurate one. We also separated the homes with central AC and the homes without central AC, because again, our hypothesis was that having central AC would essentially give you more room for improvement, and therefore you would be able to achieve a better advantage, and the results bore that out. So if you look at the results from the point of view of EUI, energy use intensity, you can see that the entire sample, if you take away the anomalies, the EUI dropped from 36.5 to 34.1. These homes, by the way, for the most part, on the small side, they were all single-family homes, all single story, somewhere between 1,300 to maybe 1,900 feet, so more on the small side. Again, the EUI dropped from 36.5 to 34.1. The homes with AC had a higher EUI to begin with, but also a larger drop. Homes without central air conditioning still an improvement, and our explanation for that was that that's probably maybe fans or maybe unit air conditioners or window air conditioners that the homeowners use, and because the temperature was slightly less, they didn't need to use them as much. Again, these results are normalized for weather, so it does take into consideration whatever differences in weather conditions may have existed in the years of the analyses. So in general, again, on average, all of our sample groups have seen a good improvement in their EUI. If you turn that into a percentage, you see that again, the entire sample except for the anomalies, so 6.7% reduction in their utility bills for the entire year, which again, specifically for this segment of the population, is not a small achievement. It can make a difference for them. Homes with AC, so 9.7, almost 10% reduction. Homes without AC, so 3.8 or almost 4% reduction. So if I can summarize some of the conclusions that we reported back out to the city, on average, we reported that the installation of the new roofs had a positive impact on reducing the difference between attic temperatures and coincident outdoor temperatures. Even in homes without air conditioning or homes that don't use a lot of air conditioning, some homes had central air conditioning, but they turn it off because they can't afford the electricity. The reduction in attic temperatures indicates that the indoor thermal conditions of these homes has improved, and that improvement, even if it doesn't lead to a large reduction in EUI, still leads to a positive improvement in their thermal comfort conditions. We also reported that the potentially negative impact in winter months didn't really bear out, that the data that we've collected show a minimal impact of the roofs on increasing heating needs in winter. At the end, we reported to the city that they have to take into consideration the size of these homes and the fact that the homeowners really don't use a lot of air conditioning, which to us indicated that if you had these roofs in larger homes or homes like mine, in which we have AC, central AC on 24/7, the potential improvement, the potential reduction in EUI could be substantially higher, both because you have a larger roof area, and therefore the impact would correlate with that, but also because, again, the impact of these roofs is mostly on the cooling energy, and if you're using more cooling energy, then the potential for improvement is that much higher. So I think that's the last slide that I have, and I will leave it there, and I'm happy to take any questions if you want. Let me stop the share.
Great, thank you, Dr. Rashid Ali. That was a great presentation. We do have a couple questions, and I think we've got some time to answer some of the clarifying questions. The first was, are these homes, the homes that were in the program, were they heated by electricity, natural gas, or some other fuel?
Almost all of them, with the exception of 2, were all electric. Yes.
Yeah. Okay, great. Another question. So in addition to the cool roofs, were any changes or improvements to the attic ventilation, such as the use of ridge vents instead of turtle vents, undertaken?
I believe the specifications of the new roof had ridge vents. Some of the original roofs already had ridge vents as well. So we didn't factor that into the analysis. But yes, the new specifications have ridge vents.
Okay, great. Third question. So in the homes that did not have air conditioning, do you have any idea how much temperature drop was experienced within the living space?
We did not measure that, but we in our surveys, several homeowners have commented on perceived improvements in their temperatures, but we did not have data loggers inside the home. We thought that would be probably difficult for the homeowners to work with.
Gotcha. And a couple questions about the energy savings. So the first question was, what is the percentage of electricity savings in air conditioning that you notice in your
we only looked at overall utility bills. That's the data that we had. However, again, since we're the only change, one of the conditions of the program is that the homeowners do not implement any other energy efficiency measures in their homes, at least for the duration of the study, for 1 year after installation. So we're fairly certain that the data that we're reporting only reflects the new roof, and the only impact that new roof will have would be on cooling energy. So I would, again, I don't have an accurate answer for that, but I would hypothesize that the majority of the reduction that I'm reporting out is a reduction in cooling energy.
Got it. And similar to that, and I don't know if this was apparent in the bills that you were looking at, but were you able to assess any of the peak power savings?
CPS Energy does not capture peak load for residential customers, unfortunately.
Gotcha. Okay.
But that would have been a very good piece of information. I agree.
The final question we have here is, and I think similar to the question we had earlier about other changes that occurred in the roof structure, was the lighter color in the shingles the main factor for the energy savings, or do you attribute the energy savings to any other factors of the new roof?
I'm sure infiltration was reduced as well with the new roof. My assumption is that the original roofs were probably leaking more than the new roof, so that's a factor in. We did not change the insulation levels, so some of these homes had insulations, some had less, some had slightly more. A couple didn't have any insulations, and unfortunately, the city didn't have funds to alter the insulation. So the only thing we did was essentially replace the roof. So I would say yes, the main change was the material, and infiltration would be a second positive impact.
Great. Okay, we have that's not a question, but it's a comment, but I'll read it anyway. It says, "I'm excited to see the effects on heating energy use has been minimal in the project."
Yes.
That is an interesting result from that.
We were actually very worried about that, because our assumption was that it's very possible that we'll lose as much in the winter as we'll gain in summer. San Antonio doesn't have really severe winters. Our winters are fairly mild, but still, we were very happy to see that the winters didn't really show a negative effect. Yes.
And I have actually one question for you related to the energy savings on the bill. Did you also report out the annual energy savings that the customers experienced in particular houses, or is that available through the work you've done?
It is available, and I'm happy to share it if you want to. Yeah, we definitely have the information for individual houses. It's not in the report that we've submit it to the city, unless you want to go through the individual graphs, but I'm happy to share it with anybody that wants to do that. There was a large variation between the individual homes, as you would expect. With energy use, that's always the case because of the many variables that impact that. But yeah, we had some homes that actually had a slight increase, but on average, again, these are the numbers that we have reported.
Oh, and then we did get one question through the chat. Can you comment on the sort of typical levels of attic insulation in the homes that you're working with?
Most of them had, I would say, maybe an R20, R25 to that level. I haven't seen all 75 of them, but I would say the ones that I've seen were in that level.
Great. Well, thanks very much, Dr. Rashad Ali. I'm very excited about this work, and thank you very much for taking the time to share it with us.
It's a pleasure. Thank you very much.
So I'm happy to introduce our second speaker, Dr. Ashwath Raman. He is an assistant professor with the Materials Science and Engineering Department at UCLA, and he's the co-founder and chief scientist of SkyCool Systems. Dr. Raman is known for founding the field of daytime radiative cooling and developing it into a nation passive cooling approach for the built environment by harnessing new optical material-based approaches. He received his PhD in applied physics from Stanford in 2013, and his AB in physics and astronomy and his MS in computer science at Harvard in 2006. He's been the recipient of many awards over the years, and you may recognize him from his TED Talk on radiative cooling and supercool materials, which he delivered in 2018, which has been viewed over 2 million times. Dr. Raman, I'm excited to welcome you. The floor is yours.
Thank you very much. So yeah, thank you again for the invitation. I'm really excited to have the opportunity to talk to this audience, which is, I think, an audience that will really appreciate and understand what is interesting and perhaps a little new in a lot of this recent work that's been happening on radiative cooling. I've kind of cheekily titled this talk Beyond Cool Roofs. I don't know if beyond is the right word, but I think for this audience, I'd really like to introduce and frame this concept of radiative cooling, as well as these super cool materials in the context of what makes them perhaps extensions of what we already do for cool roofing and cool roof type materials. And also pointing out some areas where there are some differences. Now, my own work on this has, for the most part, not been focused on roof applications or direct roof applications, but rather on using this concept of radiative cooling, which gets us essentially passive cooling that is weather dependent, but ultimately allows us to go below the ambient air temperature, both during the day and night, and hook that up directly to air conditioning and refrigeration systems. So our company, which we founded a few years ago, trying to commercialize some of this research, recently, for example, deployed one system in Southern California, which is right here. And so these panels have reflective materials that are also emissive. And the basic premise of this is that they are able to cool fluids from slightly above ambient to slightly below ambient, hook that up to condensers, the air-cooled condensers that you see right here. And when you do that, you're able to improve the efficiency of the underlying HVAC or refrigeration system about 10 or 20%. So that's been where a lot of my initial work has been. But more recently at UCLA, we've been looking at making essentially super white paints or super cool materials, whatever you'd like to call them, which have the unique property that is shared with the other kinds of radiative cooling approaches I've looked at in the past, which is that even if the sun is shining on them, they can stay cold or at least a few degrees below the air temperature. To understand why that is, I'd like to just pull this graphic up, which is from the Cool Roof Rating Council website. And if you look at this, of course, there's two pieces to the puzzle, which is that you have high solar reflectance of some value, and then you also have thermal emittance from the roof surface itself. And to introduce this concept, I begin by just asking, what would happen if we take the solar reflection of this roof surface to near 100%? Well, if we assume this thermal emittance part is just radiating into a body or an object which is at air temperature, and it absorbs and re-radiates that heat back to the surface, then you would say, Well, if we reflect 100% of the solar energy, we'll just come back down to the air temperature. But what I'm going to argue, and what is perhaps known to many of you already from various experiences, is that if you actually turn that reflection high enough, that roof surface can actually cool down to below the air temperature because of the thermal emittance. In particular, it's because of what's outside the roof, the sky. So the sky as a whole does not actually absorb and re-radiate back all the heat, especially if it's a clear day. Some of that heat that is radiated out effectively escapes to parts of the atmosphere, and some of it maybe eventually out to space. And what that means is that, in principle, if you could make that solar reflection high enough, you can actually radiate heat enough that you can cool the surface of your roof or any sky-facing material more generically to below the air temperature. So that at the heart of it is what radiative cooling is all about. It takes advantage of a natural property of our atmosphere, which actually all roof surfaces take advantage of today. And at night, it's very easy to observe. As I'll tell you later on, we observe, and especially in clear nights, especially in dry climates, like in California where I live, you will always observe that the temperature of a roof of a building at some point in the night will go below the air temperature. Now, what is the net goal then? If you can get that net thermal emittance going outwards to be larger than your solar absorption, you can then get cooling to below the air temperature in principle. There are a lot of nuances, depends on your roof, depends on the building, depends on the wind speed. There's a lot of nuances here, but that at its heart is what this is all about. And so as you might be able to tell, this then suggests something kind of interesting, which is if we take our traditional cool roof materials and crank up that reflection high enough, they should in principle not only get to the air temperature, but actually stay a bit cooler than the air temperature. This is actually an old concept, and my own work on this is certainly building on decades and perhaps even centuries of human insights into this natural phenomenon. So these buildings right here are called yakchals, and they're located throughout much of the arid parts of the Middle East and into Central Asia, and most of them are a few hundred years old. The people that operated these facilities would essentially pour water out into flat pools at night at some of these locations, and at night, even if the air temperature wasn't at freezing, the ice itself would freeze. The water itself would freeze into ice. And that ice would then be collected and stored underground for usage, potentially all the way into the summer months. And the basic reason this worked is that this pool of water was exposed in large part to the sky above it. And so while there was some evaporative cooling, the mechanism that actually allowed this pool of water to really cool down to below freezing, even when air temperatures might be 5 or 10 degrees above freezing, is because what that pool of water was looking at is the sky. And in particular, to convince yourself that this is a real and very natural phenomenon, you can point up an infrared temperature gun or take your thermal camera and point it up to the sky. Again, this will be particularly prominent when you have a nice clear day, but you should be able to measure a radiative temperature or a sky temperature that is much cooler than your surroundings. And again, the sky temperature is something that is, I think, well known and well understood in a lot of building modeling, but I'm just going to kind of recap this in case some of you may have not encountered this before. The interesting nuance here is that our atmosphere actually has a certain spectral behavior and spectral response. One way to understand it is that at particular sets of wavelengths, our atmosphere effectively allows more heat out and instead of blocking it back. Another way to think about it is in terms of the total heat that's going out from a surface facing the sky versus what's coming back to it at all angles, back from the whole hemisphere of the sky. And for a clear sky, what you'll see is that there is a definite spectral region between 8 and 13 microns, as well as at longer wavelengths. So these are all in long infrared wavelengths, where the atmosphere sends much less heat back to you than you would expect if it were like everyday materials. So all of this is to say that this is just a property of our world, right? This is a natural phenomenon. And so at night, if you put something out there with a pretty good view of the sky, it should drop to below the air temperature, especially if there are no low clouds. So especially if it's nice and clear. And if you insulate it further, you can get it to cool down to many degrees below the air temperature. So this concept had been explored scientifically for many years, including by many folks that were later in their careers became very involved in cool roofs. People like Paul Berdahl, who used to work in the Heat Island group, and it was very intriguing. And I think the main challenge it had from a technological point of view was that it worked only at night. So often it was referred to as night sky cooling or nocturnal cooling. And the main reason we didn't observe this during the day comes back to what I alluded to at the beginning of the talk, which is sunlight. Essentially, to get really meaningful cooling to below the air temperature, really you need to get over 95% solar reflectance. And at the same time, you need to make sure you have pretty good thermal emittance as well, because that thermal emittance is what actually gets you the cooling effect. The solar reflection just prevents heat gain from the sun. So those are the two pieces of the puzzle. And when we began working on it, our goal was to be able to show that this sub-ambient cooling effect that was observed naturally at night with pretty much any building material except, say, a low emissivity material like aluminum or brushed metal, that this kind of cooling effect could actually be accessible during the day. And that's intriguing, right? Because if you could get below the air temperature, you now have the potential to offset electricity you would use through a vapor compression mechanism or some other approach to get that cooling. And that's the subtle nuance I'll come back to a few different times of why cooling below the ambient air temperature has potential economic value beyond just reflecting and preventing solar heat gain. So what do we need for this to work? Well, my background comes from the world of optics and optical thin films. And in this community, which is historically not been directly involved in cool roofs and cool materials, generically, we think about designing materials from the ground up in a kind of a rational way where we essentially make surfaces that are kind of constructed through vacuum deposition kind of methods. And when we approach this problem, we observed, of course, that the same problem that anyone working on cool roofs has encountered, which is that we need to have really good solar reflection over these shorter wavelengths. And then over these longer wavelengths, we needed to have good infrared emissivity. And the infrared emissivity matters because it controls the amount of heat that is going out from that surface, and that's equivalent to the material's absorptivity. Now, this points out a subtle nuance that I'm not going to dwell on too much, but is sort of important to point out, which is that if your goal is to take advantage of radiative cooling and cool to very low temperatures, below the air temperature, to offset your cooling energy needs, not only is it beneficial to have high emissivity, but it's beneficial to have selective emissivity. And by that, I mean it is beneficial to have high emissivity within the atmospheric window from 8 to 13 microns and low emissivity outside that window. I'll come back to this in the context of super cool paints and things like that later on. But one thing to point out is that this is not strictly speaking necessary. This is beneficial if you're trying to cool down to several degrees, maybe 5 or 10 degrees C below the air temperature. But if your goal is to get a few degrees of cooling, you don't really necessarily need this selectivity. But when we began working on this, we approached this kind of from a scientific point of view and thought it would be very intriguing if we could show that we could make materials that by design had high solar reflectivity, very high solar reflectivity, but strong and selective mid-infrared emissivity within that atmospheric window, where our atmosphere essentially sends much less heat back to you. And so our original design looks something like this, and we published a paper on this. And if we look at, and again, this is all publicly available, the key results you might be interested in is that it had a 97% AM1.5 weighted solar reflectance out to about 50 degrees or so angle of incidence. And I should point out, this design consists of dielectric materials, very common materials that are used in semiconductor processing all the time, along with a backing layer of silver, right? So this is kind of like if you've thought of concentrating solar materials or mirrors, it's kind of like a unique flavor of that is unusually highly reflective. Uniquely, it has this infrared emissivity response that we were hoping to enable, which is that it's pretty decent, but not high enough emissivity, but it's sufficient for the first demonstration, a sufficiently large emissivity within this atmospheric window between 8 to 13 microns. And so in our original demonstration, what we were able to show is that we could keep this surface cool, about 5 degrees C below air temperature, even when it had about 900 watts a square meter of direct solar radiance. So this particular test wasn't done during summer months, but we essentially tilted it towards the sun during some winter testing conditions. But the key result that was very exciting to people was that this proved that you could get that key behavior of radiative cooling at night, which is that the surface stays colder than the air temperature in the middle of the day as well. And all you really needed to do was get that solar reflection high enough to make it work. Now, it's now a booming field of research. There's lots of different approaches people are trying. Some of them are, as you'll see later on, they're more coatings based. Other approaches, people are doing silvered particles in some polymer film with silvered things. But aside from all the, if you ever read articles about this, one thing I want to emphasize is that it's a very simple concept at its heart. All it's saying is that we need something that's really reflective, right? That's at its heart what it's about. Now, the infrared part has some subtleties, but for a lot of applications, even that, you just need it to be emissive, like a lot of paints are already. And for various reasons, this has attracted a lot of media interest. And I think it comes back to this idea that you can get something colder than the air temperature. If I can kind of contextualize why people have become interested in this, it's one of the few ways that we have available to us that is kind of a passive means of accessing subambient temperatures, potentially even in the middle of a very hot summer's day. So we approached this, as scientists originally, but then we began thinking about how we might actually use this technology. And so we became very interested in cooling, in directly applying this to cooling systems. And that's because they're enormous consumers of electricity. And we're became very interested in heavy duty users of cooling, like commercial refrigeration systems and data centers, which are currently responsible for about 8% of global greenhouse gas emissions. And the reason we've seen a lot of inbound interest in this kind of concept is that cooling energy demand is projected to grow by 6-fold relative to 2020 by the year 2050. And really, if this happens, we really can't reach that 1.5 C degree target. That is the hope of the UN IPCC. And the growth for use of these cooling systems is really happening in other parts of the world. In the US, we're sort of flatlining with some subtle growth here and there, but we're seeing enormous demand growth for both air conditioning as well as refrigeration systems, growth in data centers, the cold chain. So there's going to be enormous growth in both energy use as well as ensuing emissions in these systems. And so when we initially approached this, we weren't thinking about directly applying it to the roof of a building. We thought that if you could keep something cooler than the air temperature, we should plug it in directly into that underlying HVAC or refrigeration system to maximize, extracting economic value out of the material that we've made. It's staying colder. And so we initially positioned this technology as being something that could work like air-cooled systems, in that it requires no water inputs, and it has the maintenance efficiency of an air-cooled systems, but it could provide the electrical energy efficiency benefits of a water-cooled or cooling tower-based systems. And our company, when we first started, was very small, and we did some very early demonstrations like this ones, where we essentially had larger areas of radiative cooling films applied to water heat exchangers or mats that were underneath these films. And then we hooked these panels up. So this is a thermal system, not electrical, to air conditioning as well as refrigeration systems. So the idea was that we would indirectly cool the refrigerant that was leaving the condenser of either an air conditioning or refrigeration system to see how much we could improve their efficiency. And in the data we published back in 2018, what we showed was that depending on the system, we got some additional degrees of subcooling out of the refrigerant in the system, and that corresponded in this particular test to about 6 to 12% energy savings. Since then, with larger panel systems, we've shown upwards of 10 to 20% energy savings as well. So this is an example of a more recent installation. So the company has certainly grown, and we've been selling these systems to customers, our first customers. So this is a supermarket refrigeration system, which involved a 32-panel array installed in December 2019, where we compared energy use both with the panels on, which is to say there was a pump running water through these panels. And again, the panels are staying cold, so they're rejecting heat drawn out of the condenser. And comparing the savings overall. And so this, roughly speaking, so far we're looking at around 15% energy savings, which was the design target for this system. So the company is still progressing forward, and its goal is to really kind of collect more data and validate this concept and prove it to potential future users that this really works in the field and over long durations of testing. And so this is, for example, a recent installation on a roof in Southern California, where the panels are hooked up to an air-cooled system right here. You can see the roof has a lot of solar, but these panels actually tilt away from the sun slightly, about 10 degrees, and they're all hooked up thermally, as you can see right here. Now, in the last little bit of the talk, what I'd love to be able to do is kind of step back and think about what the implications of this might be for traditional cool roofs and the building envelope more generally. So a lot of the stuff I've shown earlier, the approaches we took there, which involved essentially these multi-layered optical thin films, may not be a great fit for direct application to typical building roofs. Now, one point that there are a couple of points I'd like to emphasize for applications in building roofs. So the notion of the infrared emissivity having a selectivity to it is less important typically when we're thinking about coatings on the roof of a building. And that's because when you're on the roof of the building, it's very unlikely that it's going to get substantially cooler than the air temperature. For one, it's not insulated from its surroundings. So the air will actually heat that surface back up if you start cooling down too much. On the other hand, you also might have heat flows from the interior of the building conductively as well. So when we're thinking about coatings on the roof of a building, really, we just want something that has high infrared emissivity or high infrared emittance, which is not that different from what we want with traditional cool roof materials as well. But what about the solar reflection part? Well, part of the reason we have we haven't seen materials, at least commercially available, that have extremely high solar reflection is that most of them currently absorb in the UV. So if we break down the solar spectrum in terms of the amount of intensity coming in different parts of the spectrum, there's not a lot coming in the UV, it's only about 6%. But when we need that solar reflection to be between 95 and 100%, we actually have no way out besides actually having to reflect the UV. And so let's think about what that implies then. Well, one thing it implies is we can't really use titanium dioxide because titanium dioxide is a solar UV absorber, which in many contexts is wonderful and great. But if our goal is to make something extremely reflective, it actually needs to be strongly UV reflective as well. So last year, we published a sort of a case study of a lot of different kind of pigmented paint-like approaches that could get you extremely high solar reflection, right? So basically, what we suggested was looking at wide bandgap pigments, either alumina or barium sulfate, or even PTFE, which is Teflon particles, in polymer binders. So the polymer binder we're using here is called PVDF. The polymer binder has low refractive index, and it's also not absorptive, comparatively low absorption over this entire spectrum. And when you put that all together, what you find is relative to a conventional titanium dioxide-based white paint or white coating more generically, you can boost that reflection over the UV part of the spectrum to very high values. And that these are sufficiently high values that this then allows you to make white paints that have between 95 and 100% reflection. I should mention that the notion of using barium sulfate, for example, as a super white material has been known for decades, right? Barium sulfate or some version of it, or PTFE, sintered PTFE, is used as a reflectance standards in spectrophotometers. So in one sense, there's nothing that new, but there is perhaps something new here in thinking about it in terms of actual coating or paint that we might be able to apply outdoors. And so not only using bare barium sulfate, but actually suspending it in an actual paint form factor. So we published a bunch of different examples of how you might do this, and tried to catalog what the solar reflectances were that we were measuring in our lab. So we showed some titanium-based examples that were pretty standard, 92, 93% maximum reflection that we were able to obtain in the lab, and alumina and barium sulfate versions that got up to about 97 or 98%, and then also porous PVDF versions that could approach almost 99% solar reflectance. So again, these are not commercially ready. There's a lot of R&D and issues remaining, but I think what they point to are potential mechanisms on how you can do this. One thing I should emphasize is depending on the thickness, you also get sufficiently high emittance as well, right? And so, we did some quick tests just outdoors to see how they compared in terms of their temperatures. And so we took one of our best examples and compared it to the best Cool Roof Rating Council rated, highest solar reflectance rated material we could find on the CRRC listing. And we saw that, if we just expose them by themselves on a windy day in Los Angeles under about nearly 1,000 watts a square meter of sunlight, these kinds of materials would stay typically cooler than the air temperature, only about a couple of degrees. But on average, over time, we were seeing that it would stay about 5 degrees C cooler than the best white paint that we could find commercially available today. Again, this is not to claim that this is a commercially ready product, that this is ready for prime time. But I think what's intriguing is that there's potential here. There's I think, an interesting R&D opportunity, and down the road may represent an opportunity to reimagine what cooled roofs could be, which is not only cooling relative to a dark surface, but even potentially cooling down below the air temperature and becoming part of a passive cooling strategy for the building more directly. So there are a lot of challenges here, especially if we're going down the coating route for a full building. And perhaps the single biggest challenge is durability. So none of this work, right, making this reflection higher will really matter unless that reflection can be maintained long-term. And if that reflection over time then gets back to 80%, 83%, then it's really not getting you anything different from a commercially available cool roof material today. So I think there's real work to figure out how what we can do there. And I think perhaps many people who are affiliated with the CRRC would find this of interest. I think this is something that will be essential not only for this, but for anything that's trying to take advantage of radiative cooling during the daytime, because you need to maintain that solar reflectance so high, potentially for decades. And so potentially there are cleaning strategies that are needed. There's no simple answer or straightforward answer today for these. There's also issues around glare, right? We're now proposing we get that reflection really high. It's incremental perhaps relative to 90% reflective material, but it's still a lot of glare. So our retroreflective approach is relevant here. And of course, you can think about having colored coatings which have high UV reflectance while still maintaining color as well. And all of this, of course, has potential implications for heat island mitigation, not only at the building level, but also thinking about building energy use as well, more directly. So to conclude my talk today, I'd just like to point out some other things that are happening in UCLA that you all might find interesting. One thing that a project I've become recently affiliated with is a very interdisciplinary approach to thinking about thermal comfort, so human thermal comfort in the heat island, especially outdoors. And this arises, of course, from the very real health impacts of heat. And so heat is often dubbed the silent killer. It's actually responsible for more deaths than pretty much any natural calamity you can think of. And this particular picture from a very striking New York Times article, highlights the challenges that many people face in communities here in Los Angeles where I live, which is that there's a lack of shade. And so this is a well-known and well-studied problem. And our team, which consists of 10 different faculty at UCLA, ranging from public health and policy, is thinking about interventions that could go into communities where there's not a lot of greenery today. So this is thinking beyond the building itself, whether we could create essentially shaded or perhaps radiatively cooled spaces that are substantially cooler than their surroundings, and whether that would allow for some degree, some measure of thermal comfort, even in extreme warm weather. And so we have not really constructed any prototypes or designs. This is very early stage, and it's meant to be a very inclusive and collaborative effort. We're trying to basically, take the best ideas that we can find everywhere. That includes, things like radiant cooling systems, which recently have been explored even in outdoor settings from some collaborators of ours at Princeton and in Singapore. And so we're kind of thinking, for a whole range of strategies, but how we can go beyond just thinking of greenery and thinking about whether cool roof type materials or perhaps even the super white materials I alluded to earlier could have a positive impact in a lot of these outdoor neighborhood settings in lower income parts of Los Angeles. So just wanted to say this as a pitch, we would definitely at UCLA welcome any partnerships and engagement on this concept. It's very early stage and it's meant to be a multi-year effort that hopefully we'll be able to share results about in the near future. With that, I'd like to acknowledge the many people that have worked on all the things I've shown you earlier, as well as our funding agency, and I'd be happy to take any questions you might have.
Great, thanks very much, Dr. Rahman. That was a wonderful presentation. We did get a bunch of questions. I don't know if we'll have time for all of them right now, but I do want to address maybe one or two, if that's okay, and then we can get the rest in the Q&A at the end. There were two that were combined that I think get to this issue around UV reflection or reflection of the UV portion of the spectrum. The first comment was, in the South Coast Air Basin, regulators are concerned that specific cool roofs reflect UV radiation that might exacerbate smog production. And related to that, a question about whether you've worked with any air quality modelers to look at the effects of UV reflection of your product on smog production.
The short answer is no. I think we've not really modeled the full impact of this. I think our focus has been, frankly, on just the material side. So, and I think one of your other questions point out barite reflects in the UV. That's precisely what one of the materials we've used. And there are honestly a lot of ways to do this. I think there's no one golden way to do it. I think the UV issue for smog is a perfectly legitimate one. And so it might limit its applicability in certain regions, or perhaps there's a way of tuning that as well, right? You don't, you can reduce the UV reflection based on the different composition of the particles you have and trade off with reflection as well. So yeah, I think it's definitely an important consideration. And given that there have been other groups obviously working on this, you may have seen media about this, super white paints. I think my take is we personally don't think that using barite and stuff like that isn't that a huge breakthrough, but I think that there are a lot of basic, if we want to use this, I think there's a lot of work that needs to be done. And so there are policy questions. Honestly, I think the durability question is the main one, right? If you can't maintain that reflection, then I'm not sure, that might be a deal breaker, right? So I'm not trying to like oversell anything here, but I think it's at least worth our consideration.
Mm-hmm. Wonderful. And I think we have time for one last quick question. So what maintenance strategies are you employing or planning to employ on the SkyCool systems that have already been installed?
Yeah, I think the main maintenance thing that is being envisioned right now is some kind of washing. So the materials here have like a kind of a hard coating on them, so you are in principle able to wash them. Now the precise mechanism for that maintenance process is still being worked out, so that's why these are pilots. So we're testing out different approaches, but the idea is that to try and do that for some interval that is reasonable, right? Not every week or anything, but perhaps every month or two. But part of that is understanding the degradation and reflectance, again, which has been, I think, folks in the cool roofs community know, but you kind of have to look at the degradation and reflectance over time. And for us, that corresponds to reduced electricity savings that we're delivering to the cooling system. So there's a very meaningful kind of trade-off we can make and kind of identify a sweet spot, like we can let the reflection drop a certain amount and then go in and wash it.
Great. Well, thanks very much. So we have one final speaker before our Q&A and discussion. and his name is Dr. Vivek Chandas. He is a professor of climate adaptation and director of sustaining urban places research, the Super Lab at Portland State University. He supports public, private, and nonprofit organizations in identifying and evaluating adaptations to climate-induced stressors, including extreme events like urban heat, air quality, and storms. He's published over 100 articles in 3 books, and his research has been featured in the New York Times, National Geographic, Scientific American, and dozens of other national and local media. And he also serves as chair of the City of Portland's Urban Forestry Commission and serves on several local and national advisory boards. So I'm very pleased to welcome our final speaker, Dr. Vivek Chandas. The floor is yours.
Thank you, Kurt, and thank you, CRRC. I'm a newbie here, and so I'm really getting a better understanding of all the kinds of things you're talking about. And this is kind of coming at it from an urban studies and planning perspective. So my approach is much more of focus on community engagement, as well as the planning and kind of urbanization and urban building designs discussions that we've been having. And it segues really nicely from the previous 2 presentations, and I'm really grateful to have those 2 kind of set the stage for it. I don't want to spend too much time with the kind of broad overview, but I will touch on it a little bit. Before I do that, though, I'd like to just acknowledge several folks and funders who are really responsible for this, including Jackson Vocal, Yasuo Makito, David Saylor, Joey Williams, and Minachi Rao, who've all been instrumental in kind of building this from the ground up. I'm titled this High Resolution Descriptions of Urban Heat as a way to inform building designs, and really moving towards some of the interventions that you've all talked about, whether it be specific type of roof materials and changes in albedo, or whether it be really focusing on paints and ways to be able to strategically apply some of these interventions on a broader city scale and a neighborhood scale. So that's really where I'd like to begin this. And before I do that, just kind of acknowledging the fact that we are at a time where, you know, we're seeing these dramatic shifts in climate, and the area, or at least for this audience, the area that I'm really interested in thinking about is the connection to the built environment, and specifically thinking about that with these trends already underway, we're really thinking about buildings as amplifying heat in these environments. And so we're really seeing the built environment as a means by which we can potentially turn the dial down on the experience of heat, and the role that cool roofs play, the role that interventions more generally play in being able to mediate some of the effects. And our group's really interested in current development strategies, and we're really thinking about environmental processes as part of that. My training is as an urban ecologist, and so I spend a lot of time thinking about ecosystems in the city and the ways that these environmental processes are mediated through various built forms. And so the discussions are often around private parties and the decision to build certain ways, and our codes and regulations help to inform and help to direct some of the development processes, though in large part this is done by decision makers that are outside of the public process. And so the extent of which regulations and policies programs are able to address it is still an open question, and have yet to see regulatory or any policies that have teeth to be able to mediate urban heat. And so that's kind of where we're coming into this conversation, is really thinking about this as what are municipal agencies doing to be able to combat some of the challenges that you've already heard mentioned. And so we come at this from a point of view of kind of looking at this, taking a step back and thinking about the city as a whole, or an urban region as a whole, and thinking about the conventional descriptions of urban heat that we've heard for a very long time, decades, in fact. Many of you who have contributed on this call, who have contributed to these discussions, in fact. And so we've got this for a long time. And what we can see is that, you know, we generally tend to think about this as a reference site away from the city and some point in the city where we're looking at this broad kind of dome around a city as the urban heat. And what we're doing is challenging a little bit of that in this work by using more granular ways to describe the differences in temperature across individual city streets and individual buildings at that. And generally what we've done is use weather stations and nighttime differences to nighttime to daytime differences, And we've also used a series at the bottom right image describes land surface temperature to describe variations in temperature across a landscape. And this has been done at the national, continental, and of course global scales at this point. And often, we're talking about many of the concepts that have been brought up already today: atmospheric brightness, emissivity, and where we're headed with some of this work is really thinking about how do you integrate the satellite understanding that we have with ground-based measurements. And so to get into this a little bit, we're really trying to develop predictive models for air temperature that are highly granular, or in other words, very specific to a location, an individual building, and then looking at how that may change over time across different meteorological conditions. So what we do for this particular approach is, inspired from work that's happened going back to the 1950s in Japan with folks who have looked at air temperatures in Tokyo, to more recent work that's happened in British Columbia, in various parts of the country here in the United States. We've affixed these temperature and humidity sensors onto cars. We work with community groups to be able to go out and on these pre-planned routes across an urban area, and to really get near surface air temperature and humidity for a specific location. And what that allows us to do is collect on the order of tens of thousands, sometimes hundreds of thousands of individual temperature and humidity measurements for an urban region, and getting this down to about a 10-meter resolution, as opposed to 90, or even sometimes this spatially, what we call pan sharpening to 30-meter resolution land surface temperatures. And so this gets us really right into the sweet spot of getting higher resolution, getting communities involved, which is often this process of civic legitimacy that we call, and that policymakers really respond we found very effectively to this particular approach to collecting very hyperlocal UHI data in cities. And so where we've gone with this is we've really now partnered with NOAA, National Oceanic Atmospheric Administration, and several other nonprofits in the country to really expand these campaigns across the country. And so fortunately, we've been able to now get upwards of over 40 cities, and each year we're actually building more and more of these campaigns where we have a high concentration on the East Coast, Northeast, but we're really starting to expand to the South, to the West. And while we have a big gap right now in the Intermountain West and Northern Midwest, we are slowly getting more campaigns started in each of these areas as well. So again, we're working with upwards of, sometimes in Houston and Harris County, Texas, for example, we had upwards of 150 people who were participating in this campaign, where they're driving, biking, walking, getting these very localized air temperatures in a mobile campaign. And what we do is we use a series of machine learning algorithms and a variety of different spatial analytical techniques to be able to create these high resolution surfaces of temperature across each of these cities. What we're finding is that these maps and these outputs are finding their way really quickly into a lot of the municipal climate plans that are being generated, many of which, you might note, have specific interventions, or as they're often called, specific actions, often based in the appendix of these plans, that describe approaches to using cool roof materials, or cooling, or using nature-based solutions and other approaches that are finding their way into these climate action plans. So this is the first indication that we're getting that municipal agencies are starting to take notice of this and starting to really embed some of the urban heat work directly into preparedness planning efforts within cities. Again, we have yet to see code that actually requires certain kinds of development to address urban heat, but those are, I think, quickly forthcoming. And so that puts us in this place where we're trying to get at what are the interventions that we could really start to look at when we're looking at a specific place, like in this case, Detroit, where we collected over 131,000 measurements over a particular day, and looked and developed these very high resolution heat maps of a specific location, in this case, August 8, 2020. And what we're seeing, folks like the municipality of Detroit, as well as other regions we've worked is they're really looking at these high resolution descriptions as ways to look at social vulnerability, who's being exposed. There was a great piece that came out last year in the New York Times about the relationship between heat and historic planning policies that have been put in place that have essentially helped explain why we're seeing these patterns of heat. We're seeing communities start to move into aspects of urban forestry, public health, so community resilience. And there's a bunch of direction that that's going. However, for this audience, I think what we're really interested in is the built environment and potentially housing policy or development policy more generally. And what I'd like to spend the rest of the discussion today really thinking about and exploring with you is the idea of which structural types and design features correlate with higher or lower temperatures, and then what kind of housing or development policies can address questions of density. As cities really think about density and neighborhoods get more dense, what are features on the landscape that can help to keep cities cool? And what are ways that we could actually think about that? So a few of the studies that we've been engaging in really try to get at these particular bolded items on this screen that builds off of these air temperature maps that we've been able to generate through these vast engagement campaigns around the country. So to do this, we use a complex fluid dynamics modeling platform, NVMet, and really start looking at different intervention types. Again, I know many of you are likely familiar with this approach, and we wanted to take this and put it in a real planning context. So what we've done is work with planning agencies and asking them, what are the different kinds of development approaches and codes that potentially amplify temperatures in locations, and what are ways we could use those codes to think about interventions in large urban lots, and very industrialized urban districts and suburban areas, commercial areas, and how can density applications help us better understand the role that cool roofs play, green walls, street trees, etc. So what we started with was a series of what we call, I guess, case studies where we're taking a place that is about to undergo a massive rezoning. And in this case, it was a large lot neighborhood. Each of these lots are roughly about 10,000 square feet and mostly residential. And given the development pressures in many parts of the country and world, we're really thinking about what would happen if you were to take this particular development landscape right now and increase density on this, going, in other words, from 16 units that are on that city block to 64 units. How would those variations in development or that shift in density really affect or potentially amplify temperatures? And what are interventions that could potentially keep temperatures at the same or even reduce temperatures from the higher density levels? So we use this case study to really get into this question of varying parking spaces, thinking about how these different cool roofs, as well as green spaces, as well as configurations of the development. And again, working in collaboration with the Planning Bureau design team. In this case, this particular example was done in Portland, Oregon, to try to get a sense for what was the real impact of this development. And what did we find when we ran these models on this particular lot? Well, we created a series of scenarios where we started with 64 units. All of these gray areas are 64 units, and this is the simulation output from the NVMet model, where the green is a green space, either a bush, grass, or a tree, depending on the size. The gray is a building unit. And so we tried each of these different forms, where one was a fourplex, another was a single unit, another was duplexes and triplexes put together, and then multiple multifamily residential across the board here. And one thing we really wanted to emphasize was the fact that multifamily residential is often done in such a way where developers come in and are able to use what's done for a very long time, where it's clearing the land and essentially creating this horseshoe shape with a parking lot in the middle. And so we wanted to vary that with these different plans and see how well do these models on average describe temperature at about 2 meters above the ground. And what we're starting to see as we go across these different scenarios, and Plan 6B, if you notice, is that kind of typical parking lot design, asphalt, and Plan 6S is where we essentially brought in cool roofs. We actually brought in cooler pavements surrounding the building. We brought in a lot of green infrastructure into the middle of the development, much like you might find in kind of a traditional European perimeter block design. And we then kept the base case as it would be, and tried running these different scenarios with the model. And what we were finding really quickly, and these are in Celsius here, I'm going to go between Celsius and Fahrenheit in part because of the publication process versus the community engagement process. Publications tend to like Celsius, but communities tend to like Fahrenheit, at least in the US. And so what we were finding is each of these different cases gave us an average increase in temperature of certain amounts going up until this Plan 6B, which really pronounced the temperature up about a little over 3 degrees Celsius. And what we're finding with this Plan 6S, however, where we were introducing this green space, introducing cool roofs, introducing even lighter colored asphalt surrounding the development site, we were finding actually a reduction in temperature below what we had even in the base case scenario, which was the farthest one to the left. And so that helped us really think about what might we do with different forms of development as we think through some of these opportunities for rezoning and density. And this really helped us recognize something kind of significant in that we are constantly in this conflict of more building equals greater heat. And planners right now are in a state of consternation constantly around, well, we are going to be facing some grave increases in heat in our cities, and yet what we keep building, our building structures continue to amplify them. So what we were trying to do is get a sense for, at the block scale, what could we do to reduce general temperature in this case? And we've now applied this to a series of different types of urban developments. Again, these were identified by our planning collaborators, looking at high canopy neighborhoods because some neighborhoods have a lot of trees in them. Others are urban districts or corridors. Others are medium canopy, as well as hardscape industrial or industrial districts, vegetated urban, semi-rural. And we didn't spend too much time on hillside forest because that is another story for another time. But we did look at these 6 different interventions, and we tried to give these 2 extreme scenarios to show that the way we go about making these decisions about what happens to each of these locations really matters. And in fact, one size policy for these different kinds of landscapes may not be the approach that planners want to take. And we did that through simulating 2 extreme versions. One was a massive kind of paving of each of these landscapes, and the other was a intentional greening of these landscapes. As an urban ecologist, I tend to think about green spaces a great deal: green roofs, green streets, etc. And so part of what we were looking at is how do we get at each of these with those 2 extreme versions. And what we are finding is if we take the orange, these are Fahrenheit measurements, if we take the orange as an asphalt and the blue as a greening here, a high canopy neighborhood is a HCN, and then urban district, and then large lot neighborhood, and then industrial district, and then semi-rural. These different forms or these different typologies of urban development really attenuate the extent to which an asphalt scenario versus a greening scenario may affect temperatures in these locations. And so what we were really trying to do is get at that simple fact that we might need to use different forms of interventions in different types of development. And so far it's gotten a little bit of traction. We've seen this show up in a recent code that was passed for the city of Portland called Better Housing by Design, where some of these simulations were actually directly brought into the options that developers have for advancing a heat-friendly development scenario. I want to just close out with another couple of projects that we've done, where this one was a public housing project in Washington, D.C., where we're essentially looking at urban thermal comfort and looking at what could we do in this particular location for introducing some cooling effects. And when we brought in cool roofs, we brought in greening, we brought in some of the interventions that we've just talked about and ran 3 different types of scenarios, we can actually see over the course of the day that the base case scenario can really be attenuated or really be cut off at that 4 o'clock time period in this one Greenleaf development in DC. And so what we're starting to see is actually ways to be able to simulate interventions in one individual site that allow us to then kind of almost conduct a sensitivity analysis of just the cool roofs versus just the greening versus just the trees on the sides of the building versus in the interior. And so we were able to really work with the local planners, and in this case, it was the Department of Environment and Energy to get an understanding for what interventions might be most cost effective, as well as potentially effective in cooling overall for that particular development site. So we've done this now in a handful of cities, and it seems to be still, I mean, as challenging as it is to work with NVMet, it seems to be allowing us to get an opportunity to actually talk to the planners and the developers in some cases to identify interventions such as cool roofs that could be of some value to the local community. We've been working with a group out of Lyon, France, and really looking at ways to visualize interventions as well. They have some systems that they've created that we're collaborating with. And this, for example, is looking at a train station in Paris where looking at an intervention of a green roof on that particular site allows us to then take this particular image and we've constructed some 3D models of this to allow us to look at the effect of that 3D or that green roof and the potential cooling it has using a CFD model that actually shows over time what the cooling might look like on that particular site. And again, this has been helpful more as a visualization tool, more so for getting the planners and decision makers engaged in the conversation about how these particular applications might be helpful for understanding how real temperatures could vary. So with that, I just will close out maybe by describing a few next steps. We're really thinking about the scales of intervention. As a geographer in training as well, I'm really interested in thinking about the site scale versus the neighborhood scale versus the city scale. We've done some simulations on all those and thinking about different intervention types for those scales as well. And then, of course, what has been a theme here, I think today, is these multi-sectoral collaborations to actually go in the field. And our models may say one thing, but we're working with, for example, the Urban Land Institute to set up a series of temperature measurements to see if stationary temperature measurements to see if our modeling efforts are actually proving to be correct or accurate in terms of what we're seeing at local temperatures. And then, of course, we're trying to move policies of all different kinds on this so that there can be actually some direct mandate for development types and different interventions to consider some of these cooling options for areas, not just in Pacific Northwest where we've been working a great deal, but also around the country. So with that, I'll close out. I think I'm at time here, and I'll leave some contact information here and be happy to chat with you about any or all of this. Thank you for your attention. Really appreciate the opportunity to share some of our work. Turn it back over to you, Kurt.
Great, thanks very much, Dr. Shundas. It's great to hear from you again. We did have a couple questions, a couple related to the NVMet model and maybe some more detail there in terms of how you're using it. The first was whether or not you've run into any challenges related to using NVMet to model air and surface cooling by tree canopies, and whether you've talked to George Van Weiss at USC related to that at all.
Let me turn on. So we have looked at urban canopies. I mean, that's an area we're spending a fair bit of time thinking about. This is specifically, I think, addressing urban heat. Addressing tree canopy. And so the tricky part is tree canopy on what orientation of the building, that's really played a role. We've looked at empirical evidence of tree canopy, both green space on top of roofs, adjacent to buildings, as well as in the interior of buildings, and really been able to identify the extent to which those are mediating very localized temperatures. We're not seeing a great deal of effect with, for example, tree canopy on north or east orientations, but on the west and south, for example, we're seeing a much bigger effect on temperature effects.
Great. And we had a question in the chat as you were going through and talking about the sort of integrated set of passive cooling solutions that you're evaluating. Have you looked at all at the individual measures on their own and whether you determine which have the largest potential difference on surface or air temperatures?
Yeah, we have. We actually put a paper out about 2 years ago that did a sensitivity analysis of different measures on a particular typical building stock that we are modeling in the Pacific Northwest. And one of the things we're finding is that these do have various orders of magnitude of effect for sure. And so that I'm happy to put that reference in the comment here where I can, or at least in the chat.
That'd be great. So please feel free, everyone in the audience, to type your questions into the Q&A if you've got them, both for Dr. Chandas, but also more broadly for our other panelists as well, because we're headed into pretty soon a more sort of general Q&A and discussion period here. So if you've got any open questions or anything like that, please go ahead and put them in the Q&A now. I do have one more question for you, Dr. Chandas, and you've worked with a number of cities, over 40 cities, it looks like, as part of the Heat Watch program, which is the sort of one-day big transect data gathering exercise.
Right.
And I'm curious, as you've worked with those 40 cities, have you heard what they're looking for to do next in order to characterize their heat and heat vulnerability? Are there any sort of common requests that you're hearing from cities about drilling into this further to help develop policy and that sort of thing?
Yeah, we've actually noticed that the policy uptick that's happened immediately following the Heat Watch campaigns is palpable. Like, we can actually see that there are various different bureaus within a city or that start to circulate the information that we generate, and as a result, it finds its way into the most peculiar places sometimes. We were working with Las Cruces last year, and one of the things I didn't think about, but it was only very obvious, and it actually comes back to Dr. Raman's mention of bus shelters, where the hotspots that we'd identified at this very granular scale were overlaid with the alightings and boardings of public transit, and looking at that in relation to some of these hotspots. That was one immediate way in which active transportation was brought directly into it. But what we're generally seeing is that that it's finding its way largely to public health, urban greening, and development code. Like, those are the things that we're starting to see a little more activity in right now. But again, like, some folks are looking at, for example, marathons, like Boston Marathon was using the data to try to identify hydration stations and things like that. So there's really idiosyncratic ways in which the data have been applied. Though with this particular audience, I think the cool roof approach really is where I've been trying to nudge a number of different municipalities to think a little more seriously. And there are many other groups that are involved with that discussion as well, including NOAA and various national organizations like yours.
Great, thanks. I always appreciate the shout out.
Yeah.
I'm going to turn this to more broadly, ask a few questions to our other panelists now, but if you have any other questions, please go ahead and submit them in the Q&A here. But going back to you, Dr. Raman, we had a question regarding, I guess, a more sort of overarching question, and that is, what is the significance of attaining a subambient surface temperature? That is, we certainly want to minimize net radiative heat gain, the solar gain plus long wave gain minus long wave loss. But why does it matter whether the final surface temperature is greater than, less than, or equal to the local air temperature?
In some building contexts, it may not matter, but I think where it is kind of intriguing is that it's giving you access to something you would otherwise either need to do evaporative cooling for or run an actual active cooling system to access. So it's a temperature point. Now, How you make use of that will depend on your context. Like you could imagine, not having direct thermal contact with the roof if it's cooler than its air temperature, to use it as heat rejection for your cooling system, thereby making more efficient, sort of like an analog of what the sky cool approach is. But in certain climate zones, if the temperatures are relatively temperate, you may not want as much insulation, so that you could have direct thermal contact with a roof surface that is staying cold, to keep the interior cooler as well. But in many scenarios, it may not change things too much. That's certainly fair. I think it's just an incremental reduction in the heat gain. But I think the way I view it is it's giving you access to something you would otherwise need to either do something different for, some kind of active electricity use, or alternatively do some kind of evaporative cooling approach to access, right, those temperature points. How you use it will depend very much on the specific building. And where we've seen some interest is, in certain climate zones, people who are thinking of more advanced zero net energy buildings, they're trying to ask, what if we make the roof part of the cooling system, right, directly, instead of insulating against it. Again, these are all speculative kind of one-off ideas, but I think that's the hope is on the architectural and the building design side, it might provoke some interesting thoughts from folks.
Great, thanks very much. And turning to you, Dr. Rashid Ali, I wanted to ask you, so the Under One Roof program is really unique and interesting, but it's also, I imagine, quite expensive. It's a pretty major intervention into homes, and it's been done at a fairly large scale now, 1,100 plus homes. So I'm curious how if you have a perspective on how your research and findings have helped maintain this program, which is, I think, mostly funded by the city, or what the role of public support or Councilmember Trevino, what is the sort of mix, the sweet, sort of secret sauce to maintaining programs that are important but also expensive in this space?
So the program was the brainchild of Councilor Trevino, and I would credit him with a lot of the initial push to get the city interested in getting the program started and so on. But as I mentioned, when it started, we were only talking about 10 or 11 homes. And really, that was we had about $100,000 that we needed to fit only, and we had to fit as many homes as possible. So that the most we could do was again 11 homes. But again, the goal, I think, from including the research component and collecting the data and coming back with the analysis was for us to go back to the city and kind of prove and demonstrate that there is value. So I'm fairly convinced that played a role in convincing the city to extend the program for the second year. And then after that, there was a lot of behind the scene work from the council member and other officials in the city to go to external funding sources and pitch the program, and again, use the success of the program, which included both the work that we did and many other components, including testimonials from homeowners and so on. And that allowed the city to, I believe, get a couple of $1 million donated to the project from an external entity that allowed them to expand the project to its current size. So it was a mixture of different pieces that incrementally grew. I hope that our work played a role in that. I think it's always good to have an objective evaluation of whether an idea actually works or not in reality.
No, that's great. Thanks. So this is, I guess, a question for all three of you. The one thing when I was invited to moderate this panel that really excited me about it was that you're coming at from the research community to support public policy, but also driving technological innovations, but also characterizing and addressing urban heat and working with, hand in hand with stakeholders. And each of these is a kind of a unique point of interface between the technical expert community, public policy, and the lives of we all live as private citizens. And so I'm just curious, as you're reflecting on your work with these various stakeholders that you've been working with, what has made those collaborations most effective for you? And I guess another way to ask that would be, what should the rest of us do to make the engagements with the academic and research community most valuable in terms of practical outcomes? And I'm happy to start with anybody that wants to jump in.
Well, maybe I'll start in the silence here. I guess part of what I've found to be really helpful is that we haven't gone to any community without an invitation. Like I began there with that fundamental piece of, I don't know, philosophy, I guess, or ethics that essentially says, you know, if we have a program, we put it out there, and there are communities that want to participate in that, then there is essentially a solicitation in that sense to be able to engage with a community. And so part of the collaboration begins with that idea of not necessarily going out as you know, we can often do as researchers, like research and retreat. You know, it's really to say, what is it that is needed at this particular place? What are the current, what's the constellation of existing actors in that place, and where is it that we can provide some kind of a potential insight or potential tool or a potential data set or something like that, that can kind of build up on what's already there. So I would just begin with the simple idea that it's really about not adding to the plate of what is already happening, but complementing it and trying to find that sweet spot where you are able to come into a place, recognize that there's probably a lot of work already happening there in this field, and to what role can, in our case at least, these high resolution air temperature and humidity maps provide for advancing a conversation that may have stalled in one aspect or another. And so really at that, you know, 10,000 foot level, I think that's kind of where we're operating in terms of productive collaborations.
I would agree with that completely. I think the challenge is always to figure out what can we contribute to the existing efforts. How can we, again, as was just said, how can we enhance, increase the effectiveness or complement intents or projects or programs that are ongoing, and at the same time maybe suggest additional steps, like what can, now you've done this, what can you do next? This type of work that's been done in other places that maybe could fit well here, and so on. So it's both helping the different stakeholders achieve their objectives, but also kind of informing them about what could be their next step or the next phase or what comes next, and so on. And I think if you manage to identify the right stakeholders and approach them in the right way, that could be a very effective approach.
So, you know, a couple of thoughts. I think I think I mentioned at UCLA, we recently got some internal funding for a very interdisciplinary team. So we have about 10 faculty. It's all academics. So I don't know if that entirely answers your question, but we're coming at it from very different perspectives. A lot of folks, I think Dr. Shondas probably knows, like David Eisenman and Kelly Turner, who are like doing a lot of mapping and health impacts assessment of heat in the urban heat island. And there are people like me. And then, you know, so we're, even within the academic community, I think people approach these kinds of questions from a very broad range of perspectives. And what's unique about this project is that it's very applied in the sense that our goal is to actually pilot an intervention and test it like with a partner community organization and test it and evaluate it through a whole host of metrics, and with the goal of it being a case study. And so it's actually very new for all of us. I don't think any of us has ever done something that is, for lack of a better word, kind of this hands-on and applied, because it's not necessarily about writing papers, although I suspect we will. It's about actually implementing something and trying to see if there are lessons we can draw from it that are interesting more broadly. The other point that is on the technical side that I'll make is that, you know, there's, for better or for worse, there's a lot of stuff in the media right now about super white stuff, veins, and like, you know, radiative cooling. And it's, I think, getting to the point that we need more standardization and better reporting on measurements, because again, these are mostly academic reports. So, you know, I don't think there's not like a commercial danger quite yet. Of course, whenever someone sells it, they're going to have to be much more rigorous about reporting these values. But I think there's increasingly a need for standardization in reporting these things, which are honestly, you know, I think what the Cold Roof Rating Council already does, right? And I think this already fits under that rubric. The big difference, of course, being that these aren't products yet. So for the most part, so I think but that's one thing where I think there's likely a very important need in the near future, because it's kind of a bit of the Wild West where right now where people are reporting a lot of things that gets a lot of media attention, but it's, you know, you ultimately need to benchmark everything.
Actually, Dr. Rahman, we have another question for you. During your presentation, I believe you said that sky-cooled panels were not facing directly at the sun, but were offset by several degrees. Can you explain why that orientation is chosen versus directly towards the sun?
Well, because we don't necessarily want the sun heats us up. But again, if you start tilting too much towards the ground, you don't see as much of the sky for the radiative cooling effect. So if you start tilting towards the ground, you actually get radiation from the ground, which depending on the roof surface can be a lot warmer than the sky, radiatively speaking. Honestly, the way it's tilted right now is partly because we're using some existing solar racking. But importantly, the panels are not making use of the sun, right? We actually want to be away from the sun to the extent possible. So the 10 degrees is sort of a compromise. It's not been heavily optimized or anything like that, but I think, depending on again, in the Northern Hemisphere, right, the sun is to the south. So you kind of want to tilt away from it to reduce the amount of direct sunlight, because these surfaces are not perfect reflectors by any means. They still absorb some sunlight. So we want to reduce that as much as possible. And again, that's only possible because this is not our roof surface. It's a thing we're adding on top, right, as a panel.
Great, thanks very much. I'm just looking to see if we have any other open questions here. It doesn't look like we do. So I'm going to go ahead and say, I think this is a good place to stop. I want to thank all three of our panelists today. I'm really excited to hear from each of you for wildly different reasons. So it was really great to hear your perspectives and where things are headed with cool surfaces, cool building envelopes, and how that's going to make a huge difference in how we address the climate challenges we face today and what we're facing in the future. So I want to thank you, Dr. Hazem Rashid Ali, Dr. Vivek Chandis, and Dr. Ashwath Rahman. Thank you so much for your time today and for your continued work in this space.
Thank you very much. It's been a pleasure.
Yeah,
Yep.
Thank you.
Thank you.
Thanks all for the great questions, and look forward to the rest of the member meeting. Bye all.